Hello everyone, this is Dr. Lennon and we're going over the test 2 review today. So this first one I want to look at is finding the derivative of 5x times e to the negative 3x. So we're using the product rule here. So we're going to set u equal to 5x and we're going to set v equal to e to the minus 3x. So u prime is equal to 5. And v prime is equal to minus 3e to the minus 3x. So for 5x, we're just using the derivative of a constant times x as the constant, and e to the negative 3x is the derivative of an exponential function in continuous form. So the constant multiplied with x and the exponent just comes down in front. And let's remember what the product rule says. So the product rule says if we're trying to find the derivative of uv, this is u prime v plus uv prime. So the derivative here, f prime of x, will be 5 times e to the minus 3x plus 5x times negative 3e to the minus 3x. And we can simplify that a bit by multiplying the coefficients. So your final answer will look something like 5e to the minus 3x minus 15x e to the minus 3x. And that's that. You don't really have to go any further there. Like I said, these product rules and quotient rules and even chain rules, a lot of times the derivatives become messier. I mean, you could factor out an e to the minus 3x, but we're not really trying to solve anything. So I would just stop here. So the second problem also makes use of the product rule. What we have here is, again, a polynomial multiplied now with a logarithmic function. So u is x cubed minus x squared, and v is the natural log of x. So what we want to do is, again, take the derivative just using the power rule for polynomials. So this becomes 3x squared minus 2x, and the derivative of v, the derivative of the natural log of x, is 1 over x. So what we want to do here is just apply the product rule again. And for u and u prime, since they contain more than one term, we want to remember to keep parentheses around those. So we have quantity 3x squared minus 2x times the natural log of x plus the quantity 3x squared minus 2x times 1 over x. And we can simplify that second set of parentheses by distributing the 1 over x. So this becomes plus 3x minus 2. And again, I would just stop right there. Nothing too much more to do. So the third one involves the quotient rule. So let me get that put up and then we will continue. For number 3, we want to find the derivative of 5x squared plus x over 7 raised to the x. So a couple of things here. So let's remember the quotient rule. So the quotient rule says if you want to find the derivative of u over v, this one is u prime v minus uv prime, with everybody being divided by v squared. So we want to apply that here. So we have the same setup with u and v as with the product rule, but we have to plug that into the final derivative a bit differently. So u is our numerator, which is 5x squared plus x, and v is our denominator, which is 7 raised to the x. So u prime is 10x plus 1, and v prime is, so remember the derivative rule for b to the x is natural log of b times b to the x. So this is going to be natural log of our base 7 times 7 to the x. And then we just plug that into the formula. So we have h prime of x is equal to, again, u and u prime have multiple terms, so we need to incorporate parentheses for those. So we have 10x plus 1 times 7 to the x minus 5x squared plus x times natural log of 7 times 7 to the x, with everybody being divided by v squared. So this is 7 to the x squared in the denominator. And, again, you could factor out maybe 7 to the x and expand things a bit on top, but that's really not going to make anything too much simpler. The only thing I might do here is I might use the exponent rule on the denominator. That allows me to write 7 to the x squared is just 7 to the 2x. So rewriting down this whole gigantic formula just to perform that one small simplification might seem a little silly, but I would accept either form, honestly. But again, if you have an exponent raised to the exponent, you can multiply those two exponents to remove the parentheses there. Okay, so let's continue with number 4. So number 4 is another derivative problem where we have the chain rule. So what does the chain rule say? The chain rule deals with taking the derivative of composed functions. So basically, what's going on here is this rule says if you want to find the derivative of f of g of x, what does that look like? So let me do it like this maybe. So the derivative of f of g of x, what that looks like is that is f prime of g of x times g prime of x. And if that's not super clear, that's okay, because usually I break this down as the inside function and the outside function. So if you look at f of x, the inside function we could think about as what's inside the parentheses. So that's x cubed minus 7. And then the outside function would be, imagine if you would replace x cubed minus 7 with another variable, let's say t. So this would become 10 natural log of t. So we can see that these are composed functions, because if you change t back into x cubed minus 7, you get exactly f of x, which is what we're trying to find the derivative of. So now what you do is you just take the derivative of each part using the normal rules. So the derivative of the inside is going to be 3x squared, and the derivative of the outside is going to be 10 times 1 over t, or 10 divided by t. So then what we do, so the way you find the chain rule is basically you multiply the bottom in prime times out prime, and you change t back into the original inside function. So f prime of x here is going to be 3x squared times 10 divided by x cubed minus 7. And that can be put together as one fraction. 3x squared times 10 is 30x squared over x cubed minus 7. And we could stop there. So pretty straightforward application of the chain rule. The main thing is recognizing what you are going to call the inside function. And you can always check that by replacing it as the other variable in the outside function. Usually it's whatever you would do. If you see a set of parentheses, that's often the choice for the inside function. Or if not, it might be something that you would apply first in order of operations. So let's go ahead and look at another example, number 5. So for 5, we're trying to find the derivative of, I believe this one is g of x is x cubed plus x to the 100th power. So here our inside function is again, this is another chain rule problem. So we have the inside function as x cubed plus x, and we can get our outside function by just replacing that with t. So we would get t to the 100th power. And then we take our derivatives just using the normal rules. So the derivative of the inside would be 3x squared plus 1, and the derivative of the outside would be 100t to the 99. And so, again, same thing, multiply the in prime by the out prime and replace t with the original inside function. Again, what we want to do here is because in prime has more than one term, we need parentheses around it. So we have 3x squared plus 1 times 100, and then change t back into x cubed plus x. So we have x cubed plus x to the 99th power. Now, I mean, you can distribute the 100 to the 3x squared plus 1. Of course, I don't really mind whether you keep it factored or not. I typically would just prefer to write the constant all the way in front, like 100 3x squared plus 1 times x cubed plus x to the 99th, but the previous line is fine as well. But another straightforward application of the chain rule. So nothing fancy there. You just have to recognize that x cubed plus x is being plugged into the power function t to the 100. So let's continue with number 6. So let's go ahead and see what that is. So number 6, we want to find the equation of the tangent line to the curve at the point y equals x cubed minus 2 raised to the 4th at x equals 1. So let's write that down. Find the equation of the tangent line to y equals x cubed minus 2 to the 4th at x equals 1. So there's 2 ingredients to find the equation of a tangent line. You need to know the point and you need to know the slope. So to get the point, we just plug x into the original formula. So y is going to be 1 cubed minus 2 to the 4th, which is negative 1 to the 4th power, which comes out to be 1. So our tangent line passes through the point 1, 1. Now we need to find the slope. So to find the slope, we first need to find the derivative. So what we're going to do is we're going to compute y prime using the chain rule. So let's see, our inside function would be x cubed minus 2. Our outside function would be t to the 4th. So the inside prime is 3x squared. The outside prime would be 4t cubed. So y prime here would be 3x squared times 4, and then replace t by x cubed minus 2 to the 3rd power. So basically, we don't need to worry about simplifying any of that because we can just plug in our x value to figure out the slope. So plug in x equals 1 to find the slope. So our slope is going to be equal to 3 times 4 times negative 1 to the 3rd power, which comes out to negative 12. So what do we know? Well, we know typically a line has y equals mx plus b form. So our line looks like y equals negative 12 times x plus b. So let's kind of compartmentalize this. So what we can do now is plug in the 2 values, one for y and one for x. And we just need to add 12 to both sides. And we see that the value of b is equal to 13. So 13 is equal to b. So the tangent line has equation y equals minus 12x plus 13. So that is it for finding the equation of the tangent line. So we see first we found the point, then we found the slope by finding the derivative using the chain rule, and then what we did was we plugged in the x value to find the slope at that particular time, which turned out to be negative 12, and then we just used slope-intercept form to plug in the slope and plug in the point to find the equation of our tangent line. So let's go ahead and move on to the next problem. So I believe there are 2 more. So two implicit differentiation problems are the last 2. So let's go ahead and, we do have 10 problems. So sorry, I thought there was only 8 for some reason. No, there are 10. So 2 implicit problems, and then we have, I believe, number 9 is related rates, and number 10 is also related rates. So 2 implicit and 2 related rates. Okay, so for this first implicit problem, again, we're thinking of y implicitly as another function. So whenever you take the derivative of something involving y, we also need to multiply by y prime as part of the chain rule, thinking of it as a function itself. So what we want to do here is, it's pretty easy to take the derivative of minus 5x and y squared, but the 3x squared y, we have two different variables being multiplied together, so we need to use the product rule on that term. So for the first term, finding the derivative of 3x squared y, we have u is equal to 3x squared, and we have v is equal to y. So u prime will be 6x, and v prime will be y prime. So the derivative of that first term there will be 6xy plus 3x squared y. So that's the product rule for finding the derivative of the first term. So let's just kind of scratch work off to the side. So the derivative of 3x squared y is 6xy plus 3x squared y prime, plus 3x squared y prime. Then the derivative of minus 5x is just minus 5. And the derivative of y squared would typically be 2y, but because we're doing implicit differentiation, it's going to be 2y times y prime. So then what we need to do is just gather the y primes on one side and factor them out. So we'll do that by subtracting 3x squared y prime on both sides. So we have 6xy minus 5 equals 2y y prime minus 3x squared y prime, and then we're going to factor that y prime out on the right hand side, so we get 6xy minus 5 equals 2y minus 3x squared times y prime, and then y prime is being multiplied by that parenthetical quantity 2y minus 3x squared, so we just divide on both sides by 2y minus 3x squared. So that's our answer. It looks pretty complicated, but again, we are not able to easily separate x and y in the problem, hence the need for the implicit differentiation. So this is our answer, 6xy minus 5 divided by 2y minus 3x squared. Okay, so let's continue with number 8, which is another implicit problem. So let me pause the video and write that down. So number 8 is another implicit problem, but this one, on the left-hand side, we're going to require a chain rule. So the derivative of the left-hand side, we have our inside function 5x plus y, and then we have our outside function, which is just going to be t to the third. So our inside prime, the derivative of 5x is 5, but the derivative of y is y prime, and then the derivative of the outside function is 3t squared. So our derivative of the left-hand side becomes 5 plus y prime times 3 times 5x plus y quantity squared. So that's the derivative of the left-hand side. The derivative of the right-hand side is pretty straightforward. The derivative of 6 is 0, and then minus x squared is going to become minus 2x. So what we have to do is we have to break this y prime out of there, because that's what we're trying to isolate. So really what we need to do here is let's distribute the 3 into the 5 plus y prime. So we get 15 plus 3y prime times 5x plus y quantity squared, and that equals minus 2x. And then what we want to do is we want to distribute each of these terms to the 5x plus y quantity squared. So we get 15 times 5x plus y quantity squared plus 3y prime times 5x plus y quantity squared, and that equals minus 2x. So our goal is to isolate y prime. So the first term does not have a y prime anywhere to be found. So we're going to subtract that and move it to the other side. So we subtract 15 times 5x plus y quantity squared. So we end up with 3y prime times 5x plus y quantity squared. That'll equal minus 2x minus 15 times 5x plus y quantity squared. And so to isolate y prime, what we have to do is we have to just divide by 3 times 5x plus y quantity squared on both sides. And then we'll have y prime all by itself. So y prime will equal minus 2x minus 15 times 5x plus y quantity squared divided by 3 times 5x plus y quantity squared. So it's a big old mess, but we did our job of isolating y prime, so that's how we know the implicit differentiation is finished. So let's go ahead and move on to the last two, which are related rates problems. So number 9. So for this one, we have the radius of a semicircle expanding at 1.5 centimeters per minute. How fast is the area increasing when r equals 10? So basically, the given information is we're given that dr dt equals 1.5. And what do we want? We want to know the rate of change of the area. So we want to find dA dt at the time r is equal to 10. So we need our area formula. So a semicircle is just a half circle. So if the area of a regular circle is pi r squared, then the area of a half circle is pi r squared over 2. So this is the formula we want to differentiate implicitly. So the derivative of a would be dA dt, and the derivative of the right-hand side would be 2 pi r over 2 times dr dt. Thinking of r also as an implicit function of time. So we're just left with dA dt equals the 2's cancel, just pi r dr dt. So to answer our question, we just plug in 10 for r, and we're given that dr dt is 1.5. So dA dt for our particular question is pi times, what did we say, 10 times 1.5. So that's 15 pi, which we can do in our calculator to get an approximation. So that's about 47.12. And that is going to be centimeters squared per minute. So that is it for problem number 9. So the last one is a Pythagorean Theorem related rates problem. Okay, so for this last one, we've got a ladder resting against a wall, and it's sliding down. So we've got this wall, and we've got some ladder propped against it. And basically what's going on, so we have a right triangle. The top is sliding down, so the bottom is sliding away. So for this triangle, essentially, we're just going to label using the typical variables. So the thing is, the hypotenuse never changes because that's the length of the ladder, which is 13 feet. So we can call this direction y and this direction x. So what is going on here? So we're given, they tell us what is happening. The bottom is sliding away. So basically, we're given the fact that dx dt is equal to 2. And what we want to find out is we want to find out how fast the top is sliding down. So we want to know dy dt the moment that the bottom is 12 feet from the wall. So that's when x is equal to 10, or 12, excuse me. So when x equals 12. So the equation that relates them all is the Pythagorean theorem. We basically know x squared plus y squared is equal to 13 squared, or x squared plus y squared equals 169. So when you take the derivative of the right-hand side is just 0 because that's just a constant on its own. So basically we get 2x dx dt plus 2y dy dt equals 0. So basically we want to find dy dt. We know dx dt is 2. We know we want to find it when x equals 12, so we also need to know what the value of y is, but we can do that using the Pythagorean theorem. So when x equals 12, what's the value of y? Well, we would know y squared plus 12 squared equals 13 squared. So we would get y squared. So 169 minus 144 is 25. So that means y is just equal to 5. So those are the values we can plug in. We can plug in 12 for x, 2 for dx dt, and then 5 for y, and then we're trying to solve for dy dt. So we have 48 plus 10 dy dt equals 0. So basically we're going to subtract 48 and we get 10 dy dt equals negative 48. And then we divide both sides by 10. So dy dt is minus 4.8 feet per second. So basically what that tells us is when the bottom of the ladder is 12 feet from the building, so the negative just indicates that it's sliding downward. The top is sliding down at a rate of 4.8 feet per second. So the downward indicates the negative for us. And that's it. So that's a pretty typical Pythagorean theorem related rates problem that we've seen a few of before. Okay, so that's it for the test review. Just let me know if you have any questions, and I will be sure to provide some clarification.